Hello, hello. Let's talk bonding. I love this unit. All right, you guys. So when we're talking about bonding, there are three different types of bonding that we are going to talk about in this unit. First is obviously ionic bonding. We talked about that the other day. There's also metallic bonding. I think that is a little bit of a misnomer sometimes because people think, oh, that means like one metal is bonding to another metal. When of course, really we're just talking in metallic bonds about mixtures of metals and even pure samples of metals and how they are held together. But it is noted in this chapter, so we'll go ahead and talk about it here. We'll talk about it more when we talk about intermolecular forces. And of course, our third type of bonding being covalent bonding. And I really want you guys to start thinking about these things, not just in terms of what they do with their electrons, but also their structure, because structure determines function. So when we think about ionic bonding, I automatically, obviously want you guys thinking about that transfer of electrons, which of course results in those ions arranging themselves in the crystal lattice structure. And that crystal lattice structure is what gives ionic compounds all of their properties, like that they're typically solid at room temperature. They have high melting and boiling points. They're conductive in solution. All of those properties are determined by that structure. Metallic bonding is a sea of electrons. So what's interesting about metallic bonding is it's sort of like an in-between with ionic and covalent. You know, in ionic, there's a straight-up transfer of electrons, and you end up with ions. And in covalent, you're sharing electrons, sometimes equally, sometimes unequally. And in a metal, whether it's a pure metal or a mixture of metals, which we call alloys, the electrons are sort of homeless. Like they haven't been transferred to any of the other atoms because all of the atoms are metals. They don't want the electrons. And they're not really being shared. I guess you could think about them being shared because they can move throughout the structure. But that's why metallic bonding is sort of unique, is because of this sea of electron structure where you've got delocalized sort of homeless electrons floating all around, which makes metal shiny and malleable and conductive. So again, structure determines function. What we're going to talk about today is covalent bonding, and you guys already know that covalent bonding is a sharing of electrons. And what you end up with are molecules with various shapes, polarities, and properties. So like generally speaking, covalent substances have lower melting and boiling points than ionic compounds, but covalent compounds are not always a solid at room temperature like ionic. They can be solid, they can be liquid, they can be gas. They will have varying degrees of conductivity, certainly less conductive than ionic in solution and less conductive than a solid metal. But depending on how polar they are, they might have a degree of conductivity as well. So covalent properties are going to depend not just on being covalent, but on the shape of that molecule and the polarity of that molecule. So we have to talk about that. Let's look at covalent bonding in terms of a sharing of electrons. Well, why would elements need to share electrons in order to form a bond? You would need to share electrons if both of the elements really want the electrons. Nonmetals, right? It's the non-metal to non-metal bonding that results in a sharing. So for example, if we were looking at one hydrogen atom with its one valence electron and another hydrogen atom with its one valence electron, and of course this is a 1s electron and this is a 1s electron. These two electrons, if this is 1s1 and this is 1s1, they want to be stable at 1s2. So that's not going to happen through a transfer of electrons. That's going to happen through a sharing of electrons. And so we would call that shared pair a single covalent bond. We can also say with a single covalent bond, we can say that it has a bond order equal to 1. We'll talk more about bond order a little bit later on because they're not always going to be whole numbers, and you'll see why when we start calculating these later in the unit. Well, isn't it kind of cool, you guys? Like, we learned about this last year in Honors Chem just by simply looking at the dots in your Lewis structure. But like now we can really start to look at it like in terms of quantum mechanics. If I want to look at this single bond, I could actually look at it in terms of orbital overlap. Like here's my 1s sphere for one of my hydrogens overlapping with the 1s sphere of another hydrogen atom. So this is a hydrogen 1s, and this is a hydrogen 1s. And of course, it's the attraction of the proton in the nucleus to these shared electrons and the proton in the nucleus to these shared electrons that results in this single covalent bond. You guys could also look at it in terms of like this type of quantum mechanics. If I have these 1s electrons and they come together and overlap, now I have a full shared pair, and that's going to be more stable. This is why hydrogen is diatomic. We end up with this full 1s2. We're going to have a special name for this orbital. When we start putting together atomic orbitals into what we call molecular orbitals, well, that's what happens. That's what it's called. It's called molecular orbital theory. We'll talk about that more later. Okay, let's look at another example. Let's look at one that's like slightly more complicated. Let's look at oxygen. 1, 2, 3, 4, 5, 6 valence electrons. Another oxygen next door. 1, 2, 3, 4, 5, 6. You can see where I'm putting my unpaired electrons is strategic here so that I can show, oh, look, the oxygens actually need to share 2 pairs in order to get to a full valent shell, in order to get to 8. And so this, of course, we now know is called a double covalent bond. And 1, 2, 3, 4, 5, 6, 7, 8. Right? You can count it up, make sure everybody is stable. This is a double covalent bond with a bond order equal to 2. Can we guess what I'm going to do next? Let's do nitrogen. 1, 2, 3, 4, 5 valence electrons. And listen, these do not all have to be, diatomic elements here, right? We can have a hydrogen bonded to a chlorine. That's another sort of non-metal sharing of electrons. So don't think that they have to be diatomic in order to be covalent bonds. I know you know that already. Nitrogen shares 1 pair, shares 2 pairs, still not satisfied. This looks kind of goofy here. Ooh, 3 pairs shared. Looks ridiculous. Here is our triple bond. And you can put your lone pairs wherever you want. And a bond order here. I'm just going to abbreviate it here as BO for Barack Obama. Josh, I'm going to read his book next week. I'm going to start the 700 pages. Who's with me? This is an inside joke that won't make sense to the other classes or to my classes next year watching these videos, but oh well. All right. Now, a couple of things I want you guys to know about single bonds versus double bonds versus triple bonds. So let's go ahead and scroll. When we go from a single bond to a double bond to a triple bond, generally speaking, these get shorter and stronger. Okay, so as bond order increases, bond length folks, tends to decrease. And bond strength, energy needed to break that bond, which now we know when we're talking about energy needed to do things, this is also called bond enthalpy, increase. So the shorter the bond, the stronger the bond, the harder it is to break. So bond enthalpy, we'll do a little thermo here. Bond enthalpy is, I should probably scroll, the energy needed. I'm going to say energy input, okay, because it's always an energy input. Once that bond is formed, you have to put energy in order to break it. Energy input needed to break or separate the atoms of a covalent bond. Now let's go ahead and look at some values here. So the reason why I said tends to decrease, right, is it really would not be fair of us to compare the length of this hydrogen-hydrogen single bond with the length of this oxygen-oxygen and nitrogen-nitrogen triple bond. Because according to that trend that I just explained to you, that like generally single bonds are longer and double bonds are shorter and triple bonds are even shorter, that would be if you were comparing atoms of similar radii. Now, if we think about this, we know that hydrogen, we have a 1s orbital overlap, and we know that 1s's are much smaller than the 2s and the 2p orbitals that are going to be overlapping in order to form this oxygen-oxygen double bond, or in this nitrogen-nitrogen triple bond. Okay, the valence electrons that are creating this bond and this bond are in a bigger valence shell than this hydrogen single bond. So it would be true that the nitrogen-nitrogen triple bond would be smaller or shorter is the better word, would be shorter than the oxygen-oxygen double bond because these are similar radii atoms, okay? So you can compare them. But in fact, you guys, going against that general trend, the hydrogen-hydrogen single bond is actually shorter than both of those, right? Because it's a 1s overlap. So again, we can't just look at these things with very simple, statements of like this always goes up, this always goes down. Things are more complicated than that. And now that you guys understand the quantum mechanics, and we're going to start to blend together the quantum mechanics with our understanding of bonding, I'm going to expect that you guys be able to look at this with a more discerning or through a more discerning lens. Okay, so in order to talk about this, then maybe it would be better for us to simply look at a comparison of a nitrogen-nitrogen single bond versus a nitrogen-nitrogen double bond versus a nitrogen-nitrogen triple bond. Now, in N2, we know it's a triple bond, but like let's say in some other structure or some other molecule, you have a nitrogen-nitrogen single bond. That bond length would be 1.47 angstrom. And remember, angstrom are a unit of measure that is 1 × 10⁻10th of a meter. So it's like a little bit smaller. An angstrom is like a little bit smaller than a nanometer. The nitrogen-nitrogen double bond is 1.24 angstrom. You don't need to memorize these kinds of values. I just wanted to give you guys an example. The nitrogen-nitrogen triple bond is 1.10 angstrom. So you guys can see that, for identical atoms here, as your bond length gets shorter, your bond strength is going to go up. Do I have any enthalpy values here? Oh, I don't have them handy, but we'll talk more about bond enthalpy here in a little bit. This nitrogen-nitrogen triple bond is going to be harder to break than this nitrogen-nitrogen single bond. Actually, let me pause my recording and see if I can go find some values. Aha, okay. I flipped around in my book and I found some values for you guys for bond enthalpy. The nitrogen-nitrogen single bond, which is longer, requires 163 kilojoules per mole. Like if I wanted to break a mole of those bonds, that's how much energy I would need. The double bond, that number jumps up to 418 kilojoules per mole. And the triple bond is 941 kilojoules per mole. So here you can see this general trend. But like I said, if you're dealing with something that is in a much smaller energy level, like if you're looking at, hydrogen overlap, or if you were comparing, things in the second period to things in the third or the fourth period, that can play a role as well. But if you're talking about things of similar radii, the trend holds true that when you increase your bond order, you decrease your bond length, and you increase your bond strength. Now, maybe we should look at a few very simple Lewis structures. We're going to spend our whole second half of this lecture, not today, I'm going to break it up into 2 lectures, looking at more complex Lewis dot diagrams. But I did want to just show you a couple of other ones because, I just randomly decided to do a bunch of diatomics, and that seems a little disingenuous. So let's look at a couple of others. Let's look at HF. So we'll just do some other simple Lewis structures. Now, when we do our Lewis structures lecture, I'm going to have a long series of rules that we're going to follow to get to the correct structure. But just using simple Lewis diagrams, we can eyeball these, right? Like if I have a hydrogen and I have a fluorine, it's very easy to see. I don't have to follow a whole bunch of crazy rules or anything. Not that they're crazy. I hope you guys like those Lewis rules. I do. You can see very clearly, like, oh, look, if they share, the hydrogen will be satisfied with 2, and now the fluorine will have 1, 2, 3, 4, 5, 6, 7, 8. So, like, I don't have to do much to land myself at the Lewis structure for hydrofluoric acid. Let's do another simple one. Let's do NH3. So if I've got a nitrogen with 5 valence electrons, you can see here I have 3 homes for 3 hydrogens. A bond there, a bond there, and a shared bond there. We all know this, common name ammonia or nitrogen trihydride. Oh my gosh, you guys, do we need to go over covalent nomenclature? I hope not. Remember, we use prefixes and everything ends in "ide." Boom. There you go. Nitrogen trihydride. We don't use mono for the element at the top. Not the top. The first element. We don't use no mono on the first. Okay? This I named as an acid because it is one. All right. What else should we do? What about water? Oxygen with its 6 valence electrons. 2 homes for hydrogens. There's going to be a hydrogen over here. And there's going to be a hydrogen over there. Now, we, of course, know this is going to be bent. Do we want to start doing geometries, too? I mean, why not, right? Previewing our next chapter. Dihydrogen monoxide, right? So we do use mono on the second name or on the second element in our name of our compound. And one more, shall we? Carbon with its 4 valence electrons. Homes for 4 hydrogens. 1, 2. They don't always have to be hydrogens. Ugh, gosh. See, I just keep doing things that are, they could be chlorines. Anything with 1 valence electron available to share, right? Could be filling in here. This is CH4. It's going to be tetrahedral. Now, you might want to call this carbon trihydride. Carbon-based compounds have special organic nomenclature. We kind of talked about it a little bit in the summer work, I think. This would be methane. So we will be using some common names and some organic names for substances with carbon. They're going to be organic. For this nitrogen, there's a common name of ammonia. And of course, we also have the common name of water. This is an acid. Okay, so what you guys can see here is that there are some very simple Lewis structures where you can just eyeball it and see who needs to share electrons in order to get to that full valence shell of 8. And then, of course, we know this gets much more complicated as we start looking at more complex Lewis structures and resonance and formal charge, all that stuff. But we'll save that for lecture number 2. Okay. So what do I want to talk about next? Not all of these shared bonds are created equal. In other words, when these electrons are being shared, sometimes they're being shared equally, and they sit right smack dab in between, in the middle of those two atoms. But sometimes one of the atoms loves the electrons more than the other atom. And so those electrons shift towards the atom that wants the electrons the most. Now, they don't get totally transferred like in ionic, but they're spending more time closer to the more, do we remember the word? The more electronegative atom. Let's talk about it. So this, of course, is one of the trends on the periodic table that we didn't talk about in our last unit when we were talking about trends, because we wanted to look at it in the context of covalent bonding. So let's remind ourselves. Here we are in covalent bonding. Electronegativity, I abbreviate as love for electrons. It's like which atom loves the electrons the most. Now, technically, electronegativity is a measure of how much an atom is able to attract the shared electrons in a bond. If you have atoms with large differences in electronegativity, okay, so if you have a big difference in eneg, I'll abbreviate, big difference in electronegativity, you're going to end up with an ionic bond. Because what that means is that one atom really loved the electrons and the other one didn't. They were willing to just transfer. If you have a moderate difference in electronegativity, your bond is going to be polar. Now, we can talk about relative polarity, like you can have strongly polar and you can have weakly polar. So obviously, the bigger the difference in electronegativity, the more polar that bond is. And then if you have no difference, like small to no difference in electronegativity, your bond is going to be non-polar. Okay, so there's 3 different types of bonds out there: ionic, polar, and nonpolar. Now, of course, polar and nonpolar are only for covalent bonds, you guys, right? If they're sharing electrons at all, they are covalent. So you'll hear me say polar covalent and nonpolar covalent. All right, now, today we are only going to look at bond polarity. Bond polarity is a measure of that difference of love for electrons between just 2 atoms, okay? Looking at the individual polarity of the bonds between 2 atoms. So today we are going to look at the polarity of bonds between two atoms in a molecule. Now, the reason why I highlight that and say that, right, is because it turns out that, yes, the polarity of the bonds in the molecule matter, but depending on the shape of that molecule and the arrangement of those bonds in the molecule, the bonds might be polar, but the molecule as a whole might be nonpolar. Remember how those polar bonds can cancel out? So in order to talk about molecular polarity, or the polarity of the molecule as a whole, we're going to have to talk about shape. And we're not there yet, okay? Molecular polarity is going to be discussed in chapter 9. Molecular polarity looks at how the shape of the molecule can play a role in determining overall polarity. In other words, the spoiler alert here is that polar bonds can cancel out and result in a nonpolar molecule. Okay, but we're not going to worry about that right now. Let's just look at bond polarity. Okie dokie. Should I make up some examples? Actually, no, maybe I'll use the examples from below. Let's use F2. There we go. All right, so let's use F2. The F2 molecule looks like this in terms of our Lewis structure. Let's go look at the electronegativity values for fluorine. Oh, that blue is not bright enough, is it, you guys? Sorry. I need something really bright, but a different color. Purple? Make it brighter. All right. Fluorine has an electronegativity value of 4.0. And this guy has an electronegativity value of 4.0. They're playing tug of war with the same amount of strength, right? These electrons here in this shared bond are being pulled, with a sense of like a 4.0 to the left and a 4.0 to the right. It would be like clones playing tug of war. Nobody's going to win. The electrons are going to stay right smack dab in the middle. So if you look at the difference in electronegativity, 4.0 to 4.0, there is no difference in electronegativity. The electrons are going to be right smack dab in the middle of the bond. There's going to be even electron cloud distribution. If you wanted to look at it like this, like here's one nucleus and here's the other nucleus, the electrons are going to be evenly distributed around that molecule. That is a non-polar bond. Okay. Let's save that color. How do I save this color? Oh no, now I'm messing with my brush size and everything. Hopefully I'm off camera. You guys can't see the struggle that I'm having. All right. I need to go back to my green. Here we go. Let's look at HF. I'm never going to find that color purple again because I wasn't able to save it. Let's try. All right. Fluorine, we know, 4.0. Close enough. Hydrogen has an electronegativity value up here, 2.1. So a 4.0 minus a 2.1 is an electronegativity value difference of 1.9. That's a pretty significant difference. In fact, we tend to say anything greater than that, any difference greater than 1.9 would be considered ionic. Okay, so in other words, the electrons in this bond are being pulled really significantly towards the fluorine. This is my polarity arrow. You guys see how I just drew it with a little tail on the end? This is how we indicate polarity in a bond, is with an arrow pulling towards the more electronegative atom. We also put a funny little symbol on here. Looks like, I don't know, music note or something. This fluorine is going to become partially negative. Okay, so this sign means partial charge because the electrons in this shared bond shifted towards the fluorine. So the fluorine is going to become partially negative. The hydrogen is going to become partially positive. So the electron density, and this is why I have the drawings down below because my drawings just are terrible. I can never draw these. I want to show like, it always looks like a messed up peanut or something, like an ugly turtle. Okay. I'm trying to show more electrons over here on this side of the molecule, right? They've been pulled over here, and so your electron density is going to be a little bigger over here on the fluorine side. This side's going to be partially negative. This side's going to be partially positive. This is a polar bond. And if your electronegativity difference was so great, like let's say, what was this one? Lithium and fluorine? Yeah, lithium and fluorine. Of course, I've run out of room. Whatever, I can go down here. Lithium and fluorine. Now, I'm not drawing them sharing those electrons because I know metal to nonmetal is going to have such a big difference in electronegativity values that it doesn't matter. I'm not going to be sharing electrons. I mean, it does matter that there's a big difference. What did we say fluorine was? Fluorine is 4.0. Lithium, 1.0. This difference is really great. Difference of 3. This is going to be ionic. Okay, so if you have an electronegativity value difference greater than 2, it's ionic. All right. And you know what? You don't even have to bother with that. As soon as you see metal, nonmetal, you know that is going to be a transfer of electrons right there. And what you're going to end up with is lithium with a 1 plus and fluorine with a 1 minus with that extra valence electron. So you're not going to be showing any sharing of electrons at all. That electron just got straight up transferred, and you've got this charge. Ionic. Oops, I already wrote that. Okay, let's take a look at some better drawings than mine. Let's look at some like actual electron density clouds here. So you can see when we have a non-polar covalent situation, you've got equal electron densities around each nuclei. The electrons are being shared equally. If you have a polar covalent bond, you can see these electrons are shifting towards the more electronegative atom. There's my polarity arrow. Partially negative, partially positive. We say that this molecule has a dipole moment. Dipole just means 2 poles. 2 poles. What are poles? Areas with charge. The whole dipole moment thing confuses everybody all the time. They're like, what's a dipole moment? It's like a molecule with 2 areas of charge. Now, of course, you know, I said we weren't going to talk about molecular polarity, but in this case, the molecule is only composed of those 2 atoms. So I can go ahead and start talking about the molecule here. In an ionic compound, you get the full-on transfer of electrons. Okay, and they changed colors to red here to show that the electron density is actually much greater here than it is here in blue. Okay, so lighter electron densities in blue, heavier electron densities in red. So you can see blue to yellowish. When we go to red, it means that's where all the electrons are. All the valence electrons at least, right? So we showed that transfer. This would have a full 1 plus. This is now our cation. This would, oh my gosh, Amanda, honestly, this would be a full 1 minus, being our anion. This would be a full 1 plus our cation. So that's the difference between polar covalent and ionic. A full transfer of electrons, a full magnitude of charge, none of this partial nonsense going on. It's not nonsense, it's important. So let's talk more about these dipole moments, okay? We can actually calculate the dipole moment, or like how strongly the electrons have shifted to one side of the molecule or another. So a dipole moment is an area or areas on the molecule with charge. And you can actually calculate the dipole moment, or how strongly partially positive or how strongly partially negative that particular bond is. So it's a measures just how polar a bond is. So the equation to calculate the dipole moment is equal to Q times R. The dipole moment is equal to the magnitude of the partial charge times the distance between those charges. So of course we know the bigger the charge, right? Like if our charges are bigger, my pen froze. If the charges are bigger, the dipole moment is going to be bigger. Okay, and we're not going to actually have to be able to calculate these things, you guys. You know, I know in your textbook, I'm looking at your textbook right now here. There's some example problems, but like the AP test actually I've never seen any question on the AP test where it actually asks you to calculate it. I'm just trying to decide if we want to do that or not. No, it's not like it's hard or anything. It's just like a multiplication value. Yeah, no, we don't need to bother. What I want you guys to be able to recognize with dipole moments as we look at these particular compounds here, these acids with the halogens, hydrogen to fluorine to chlorine to bromine and iodine. I want you to think about how all of these things sort of relate. So what you're seeing here, when you go down this group from fluorine to chlorine to bromine to iodine, their radii get bigger, right? We know that. When you go down a group, radius increases. So if you're getting this increase in radius of the atoms, do you guys see how the bond length, you're going to get an increase in your bond length? So the atoms are getting farther apart from one another. And you might think that because you're getting this increase in bond length, or this increase in the distance between the charges, this R here, that would increase your dipole moment. But the reason why it's not in this case is because we have these two competing forces here. Right? We do have two competing forces. We have charge and we have distance between those charges. And those both matter. So what you're seeing here is that the electronegativity difference is so significant that fluorine is way more electronegative. Oh my God, I forgot to talk about the trend. We'll go back and do that. That the electronegativity difference here makes fluorine way more polar than chlorine, because the electronegativity difference between hydrogen and fluorine is much greater. So you're going to have a much bigger magnitude of charge, right? So it's going to be this value that's sort of overriding the fact that the radius or the distance between the charges is small. Okay, so here you're going to have the bigger dipole moment. So what we're seeing here is when you get this increase in electronegativity difference, you're essentially getting an increase in the partial charges, which is resulting, now I'm talking about going like up a group, sorry, that was confusing, You're going to get an increase in magnitude of the dipole moment. And so the bigger the dipole moment, the more polar that bond is. So these bonds are more polar and these bonds are less polar. And that's because up here you have a big difference in electronegativity, and down here you have a small difference in electronegativity. Okay, I forgot to talk about the trend in electronegativity. Whoopsie. Let's go back. Let's look at our periodic table here. Please notice that all of the metals, especially these metals here on the left with their 1 and 2 valence electrons, they really want to lose electrons. They do not want to gain electrons at all. They have very low electronegativity values, right? So the metals have low electronegativity. Take a look at your nonmetals. Your nonmetals, obviously, have high electronegativity. But what we're really comparing in these covalent bonds is nonmetal to nonmetal. So now we got to kind of look for the trend. And what you see is that you get an increase in electronegativity, generally, as you move from left to right, and a decrease as you move top to bottom. So you get an increase across a period, but you get a decrease down a group. And that has to do with radius, right? As radius gets smaller, you can see here fluorine, now not the smallest radius, helium has the smallest, but we'll talk about that in a minute. Smaller radii are able to attract electrons more strongly because they can snuggle up next door to them. So fluorine is your most electronegative atom on the periodic table, and you can see here that nitrogen, oxygen, and the halogens are not far behind. Okay, those are going to result in really polar bonds when they're bonded to things like hydrogen or carbon. You're going to get a big difference in electronegativity. Now notice the noble gases all the way to xenon, they don't have electronegativity values because they don't bond. Neither does radon. Xenon can be forced to bond, okay? So xenon, in fact, does have an electronegativity value, but the other noble gases don't bond, so they have no electronegativity values. And that is the trend. Is that all I wanted to talk about? Oh, no, I think I wanted to talk a little bit about bond enthalpy. So I'm going to pause and make sure I have some handy values here for us before we talk about that. Okay, guys, let's continue. Last part for today before we do our more complex Lewis drawings. I talked a little bit earlier about bond enthalpy. Now remember, bond enthalpy, you already wrote this down, is the energy needed to break a covalent bond. I almost just wrote, I forgot the B in break. Great. To break a covalent bond. And so that's useful information and all. But what's really cool about bond enthalpies is that we can actually use them to calculate the enthalpy of a reaction. Delta H reaction. We already know 3 other ways to do this, right? We know that we can use calorimetry. That's such a hard word for me to say. With our Q equals MC delta T. We know that we can use heats of formation. We can get a heat of a reaction by doing the sum of the heats of formation of the products minus the sum of the heats of formation of the, oh my gosh, what is wrong with my handwriting all of a sudden? Heats of formation of the reactants. We also know that we can use Hess's law. Didn't you always want one more method? Let's do it. One of the ways that we can get the delta H of a reaction is take the sum of the bond enthalpies, sorry, needed a sum sign, the sum of the bond enthalpies, D. Oh, sorry, bond enthalpy, you guys, is D. The bond enthalpies of the bonds that are broken minus the sum of the bond enthalpies of the bonds that are formed. Now, people, when I give them this equation, they start to mix it up with this other equation for a couple of different reasons. Reason number one is I wrote bonds broken because bonds broken are actually the bonds, you guys, of the reactants. And in every other equation we do, you guys, it's products minus reactants. And here it's reactants minus products. You'll see why once we do a calculation. Okay, so don't let this mess you up for every other equation that we do, which is always final minus initial, always products minus reactants. This one is bonds broken minus bonds formed. Bonds formed are your products. Here's the other thing that messes people up. They're like, we're not breaking the bonds of the products. I know you're not. I know you're making them. But we're not talking about the energy released when a bond is made. In order to get the delta H of a reaction, okay, we need to look at the differences between what it takes to break the reactants versus what it would take to break the products, and that's the difference. So yeah, we are comparing what it would take to break these bonds, even though in the reaction we're making the bonds, okay? Because we have to be comparing the two of the same things in order to subtract them. So how much energy would it take to break these bonds versus how much energy would it take to break those bonds? That's the delta that's going to be absorbed or released by the reaction. It's the same thing as up here, you guys, except here we're talking about energy of forming that stuff versus energy of breaking that stuff. Okay? So don't confuse it. All right, so here is our fourth way to calculate the heat of a reaction. Now, of course, you would have a chart with all of the values of the different bond enthalpies. So let's do an example problem, even though you don't have a chart handy. Actually, you do. I think I gave you one in your pile of resources. So you might actually have a piece of paper that says bond enthalpies on there. But if not, you can just take my word for it. All right, let's try to get the delta H of the following reaction. All right, we're going to do CH4 reacting with Cl2 to produce CH3Cl and HCl. We want to know, what is the delta H of this reaction? First of all, we need to make sure we're balanced. And luckily we are. Now, I probably should have picked an example where we had coefficients, because the coefficients are going to matter. Should I pick a different reaction? No, then I got to go look for different values. All right, just know, hopefully there's a practice problem that you're doing in your packets later that has coefficients, because if there's a coefficient, that's going to affect the number of bonds that are broken and formed. Okay, so here's the thing with these, you guys. You got to draw your Lewis structures, because you actually have to count up all the individual bonds. And that's why, if there was a coefficient in there, let's say there was a 2 out in front of this methane molecule, instead of 4 hydrogen carbon bonds, you would have 8 of them. Okay, so pay attention if you had a coefficient. All right, this chlorine to chlorine we know is a single bond. I'm not even going to draw in my lone pairs. All right, we've got 3 hydrogens here and a chlorine. It's going to have lone pairs on it too. Who cares? We just care about the bonds. And we have an HCl bond. Okay, so I need to, oh my God, I can't scroll down. Shoot, that's annoying. I'm going to switch colors here. All right, I've got 4 carbon hydrogen, 1, 2, 3, 4 carbon hydrogen single bonds. So if I need to sum up the enthalpies of my bonds that are being broken, I need to take into account those 4 carbon, hydrogen, single bonds. And I need to add to that this 1 chlorine-chlorine single bond. These are the bonds that are being broken, reactants, minus the sum of the bond enthalpies of the bonds that are being formed. Now I get it. We're not breaking these bonds. We're making these bonds, but it doesn't matter. Look up their bond enthalpies. We're going to do 3 carbon-hydrogen bonds plus 1 carbon-chlorine bond. Okay, so it matters here, right? Like a carbon-hydrogen bond doesn't have the same enthalpy as a carbon-chlorine bond, so pay attention. And this hydrogen-chlorine bond, 1 hydrogen-chlorine bond. Okay, so now I just go look up these bond enthalpies, you guys. The bond enthalpy for a carbon-hydrogen bond is 413 kilojoules. And again, it's per mole. These are moles, right? If it's a 1 to 1 to 1 to 1 mole ratio. Again, if there were coefficients out there, take them into account, right? Like if there was a 2 out in front of this Cl2, you'd have to add 2 of those bonds. Plus chlorine-chlorine bond, 242 kilojoules. Minus. Now listen, if you guys had wanted to reduce, do you see how you'd like 4 carbon hydrogens here and 3 carbon hydrogens there? If you wanted to just like reduce those and only have 1 carbon hydrogen over here, you totally could have done that. But whatever, I'm a simpleton, so I just do this. I just plug it all in. All right, now we've got a carbon-chlorine bond. That's different than a chlorine-chlorine bond. Why can't I find it? Oh, phew, 328. That took me forever. Plus a hydrogen-chlorine bond. $431. Ugh, and all of a sudden I stopped using units. Kilojoules. All right. Let's knock this out. And then watch your minus sign there, right? Now we're subtracting the products. Nope. Yeah, the products. 3 times 413 minus 328 minus 431. I get negative 104 kilojoules. Oh, look. That's that right there. The delta H of this reaction is equal to 104 kilojoules per mole released. This is an exothermic reaction. So all you got to do is compare the amount of energy it would take to break the bonds of the reactants versus the amount of energy it would take to break the bonds of the products. The delta between them is the delta H of your reaction. So think about this, right? If I end up with a negative value here, that means that this value, the bond enthalpies of my products, were greater. It would take more energy to break apart my products than it would to break apart my reactants. That must mean that in this reaction, the products are more stable. Let's look at an energy diagram here. If my products are more stable, they're lower in energy. If my reactants are easier to break, they are higher in energy. What do you guys see here? Look at products minus reactants. That would give us a negative delta H. The AP exam loves to have you guys make this connection here. If the products have a bigger bond enthalpy than the reactants, the products are more stable, lower on our potential energy diagram than the reactants are, and so this reaction is going to be exothermic. That's why, you guys, we have to do reactants minus products here when we're talking about bond enthalpy versus products minus reactants. Oh gosh, should I say this one backwards? Who knows? Why we have to do products minus reactants for the energy of formation in order to get a delta H that is positive or negative, respectively. And I think that is all. All right, you guys, you have some exercises to go do, and then we will do another lecture with all of the really fun different Lewis structures. See you then.